I can reshare.
No, it's okay. You're sharing.
Okay.
Don't worry. I had you behind the live stream window. All right, there we go.
And 1 minute to the hour, I'm about to go live on YouTube.
Open the chat and the QA boxes.
Okay, and we're live. Okay, welcome everyone to the You Can Build Your Own Models. Why don't you need to be scared of doing your own data science? An Energy and Data webinar series. Dr. Siddharath Mishra is the co-chair of the Energy and Data webinar series committee, and I am Annabella Betancourt, and I will serve as your host today for the webinar. Before we begin, I want to establish some rules. We're going to have a 40-minute presentation. This presentation is scheduled to be given in 2 parts. After the first part, I will open a 5-minute question and answer session, and then we'll continue to the second part where we can address the rest of the questions that you may have. We will appreciate if you send your questions through the Q&A button that is at the bottom of your screen. Please do not use the chat to send the questions, as they may get lost. Today, we have Keith Moore with us. He is the Director of Product Management at Spark Cognition and is responsible for the development of the Darwin automated model building products. He specializes in applying advanced data science and natural language processing algorithms to complex data sets. He has multiple patents in the space of data science automation software and has been recognized by the Hart Energy as an influencer in the energy innovation space. He also previously worked for National Instruments as data acquisition and migration software product manager. And prior to that, he developed client software solutions for major oil and gas, aerospace, and semiconductor organization. He has served as board member of Pi Kappa Phi fraternity and still serves as volunteer in the Alumni Engagement Committee. He graduated from the University of Tennessee with a Bachelor in Science in Mechanical Engineering and serves on the Alumni Board of Advisors for the Austin, Texas area. We're very excited to have him here today for this presentation. Just a note for you, the material that we're presenting today is copyrighted. All rights belong to the author, and we will appreciate that you do not record this webinar. It will be streamed live and also made available later on in the Energy in Data page, webpage, and YouTube channel, so you can access it later through that media. Next. Energy in Data, for those of you who are not aware of it, is an event that has been put together by 3 societies, AAPG, SPE, and SEG. And is an event that is meant to gather professionals from multidisciplinary teams, geoscientists and engineers, from small and large oil companies, academia, and research, so we can define the future of the digitalization for the oil and gas industry. It's meant to be a collaborative event, and where you can share your thoughts, lessons learned, and best practices, so we can progress the science according to what the oil and gas industry requires, and with the influence of other industries outside of oil and gas. The next event that we will be holding will be in Austin in February 21 through the 24th. And we hope that you can join us there. Otherwise, we have a whole series of webinars that you can enjoy. Once per month, we will be releasing new subjects for the community to learn and get engaged in digitalization. And with that, I open it to Keith.
Awesome. Well, thank you so much, Annabella. Thank you so much to the whole team and the energy and data team for letting me be here to present to you guys. There's a lot of folks on the line right now, and I know that there's a global presence watching in on this. So just to reiterate, I put this together for you guys. And so if you do have questions, please use that Q&A section. I'm going to try my best to get to everything. If I don't have a chance to answer your question and you have other questions, whether it be about the technology or something that you're working on, as you'll hopefully be able to tell, this is something I'm very passionate about. So feel free to reach out to me, whether it be on LinkedIn or any other medium. And I'm more than happy to take your questions there as well. So when it comes to machine learning and AI, these are very buzzword heavy items to where they've almost been used so frequently that it's challenging to tell what they mean. But whenever you go to an AI presentation, and I use the air quotes intentionally because of that, there's really two ends of the spectrum that you run into. And the first one is, I need AI. It's going to solve all of my problems. It's this magic technology that enables us to somehow do things better. And then there's the other end of the spectrum, which is I'm going to present my 20-page scientific research paper on, why learning rates should be modified in order to improve efficacy of certain types of neural network architectures. And so the good news, hopefully for you guys, is in this presentation, we're not going to really hit either end of the spectrum. The goal is to be in the middle. So I'm a mechanical engineer by training. I do not have a PhD in machine learning. I definitely know enough to be dangerous. But my hope for today is to give you a good feel for what it is, how it practically ties to business, and some of the different pieces that a data scientist is actually thinking about. So if you want to go and do this yourself, you're able to. So there's two core agenda items. And as Annabella mentioned, there's going to be two parts to this presentation. The first is a deep dive into machine learning. And when I say machine learning, this is the process of using mathematics to adapt models to data in order to achieve some outcome. And then the second piece is, how do we translate that machine learning to a real problem? So can we take this math and actually make it useful for a challenge that a business may face? So realistically, we're talking about things and thinking about things that either make more money, save more money, increase the welfare of employees, or increase safety. There's a variety of different drivers, but at the end of the day, there has to be a core objective for the business that uses machine learning. It's not just a technology you can drop and magically make work. So before we get started, I want to conduct a quick poll because to me, it's really important. I can actually present this a variety of different ways. I want to get an understanding of the mix of personnel that we have here. And so really your knowledge of machine learning. So I'll give it just a second for you guys to take this poll. And then we can take a look at the results, and I can adapt everything I say from here on out for what you guys want to hear.
We're 45% into the poll, 70%.
Awesome. Thank you, guys.
Okay, so it seems 78, 79, 80. Let's give it a few more seconds for people to vote. We're at 83. And it seems that's gonna be it. So I'm gonna share the poll results. Are you able to see them?
I am not.
Okay. So we got about 43% with novice learning or knowledge, about 50% of the audience has intermediate knowledge, and about 7%, which is 15 people, with expert knowledge on the subject of machine learning.
Excellent. Oh, there we go. And here it appears. Perfect. Well, thank you so much, Annabella. Thank you for everybody who voted. Very much appreciated. That helps me a lot. So what I'll do is I'll tailor things to the novice intermediate section. If there are, some of the 15 folks that voted as experts, if you have more particular questions, please do not hesitate to ask them. I just will likely try to answer them fairly quickly. And if we wanted to carry that conversation offline, we absolutely can. So let's go ahead and keep going. So let's start with the machine learning deep dive. When I say I'm engaging in machine learning, what does it actually mean? And really what that means is I'm taking data and transforming that data into a model. That model is a representation of that data and can be used to better understand what's happening in the world, better understand segments of that data, or create predictions for the future. Before we get into, all of the steps of machine learning and AI, the first thing is like, how does this fit into a business model? And this is what I call the practical side of AI. We're looking at organizationally, how are groups set up and what processes do they engage in order to take AI and make it feasible and real for solving business problems. And it always starts with some form of question being asked by an executive team. In some cases, this is a little bit more rare now than it was 5 years ago. They'll say, I need AI. But more frequently, they say, hey, we have a team that may be dedicated to machine learning, or we have some consultants we're working with that know a lot about machine learning. How can we solve certain problems? And they'll actually say, there's a large macro problem, like, for example, in the finance world, how can we make more money from our lending business? And then it's on the directors, VPs, managers to actually ideate a little bit and say, well, there are certain more nuanced things and specific items that we can actually do to try and improve that business objective of making more money or saving more money. And so they'll ideate on a few, and eventually they'll say, if we do like an initial ROI or return on investment calculation on these, here are the few that we think are probably most promising. Let's pass these over to our analytics team or our data science team and begin experimenting. And so this experimentation phase is critical because we say, we have this idea, we think that there is some return on investment that we can get, and we can quantify that for the business. And then we actually see if we can make that a reality. So now it is a data engineer, data analyst, data scientist who is looking and saying, do we have the appropriate data to solve this problem? How can we set up this problem and this data to actually create something predictive or valuable? And they're going to iterate in this process. It's not just okay, here's the data, here's the model, we're done. This is something that requires a lot of different feedback and a lot of different inputs, whether it be from the technical team or from the line of business. And this is honestly where most things die. I would imagine a lot of you in the who have some intermediate experience with analytics have seen a lot of projects kick off, but after they're kicked off, they might see some results and they may see a report, but it never actually makes it to what I call production, which is we now have that report, we have that knowledge, and we want to take that and deploy it into the real world. So we are actively using that mathematical representation, that machine learning model, to continuously create predictions in real time to actually drive value. And so that's that next step, which is operationalizing the model. Once we have something that is good, we basically spend a bunch of time experimenting and building a report on saying, here's what we think is feasible, and here's what the return on investment we could get actually is. We have to take everything that we did and put it into an operational platform. That's that blue box. And so that operational platform is now no longer looking at a static data set. It's looking at data, whether it be every second, every minute, every day, every week, every month. And it is dynamically creating predictions on those and then presenting them in that red section in a dashboard that's useful for whoever needs to take action on them. So that's really an end-to-end machine learning system, is not just the idea, not just the experimentation and report, but an end-to-end system that is in real time or near real time, creating predictions that are valuable and actionable. And so where the value in this is, you can see this red arrow that actually goes from the business dashboards back to the experimentation phase, is that the whole concept of machine learning is that it is dynamically learning from data. So when behavioral patterns change, when the data changes, the models are actually able to continuously adapt and relearn how to best solve that given problem and grow over time. Get smarter over time is often how it's phrased. And so that's really what the objective of a machine learning and AI system is. And when you put it like this, it seems kind of straightforward, but the thing I'm not covering is most frequently there are anywhere from 3 people to a few dozen people responsible for different touch points in this process to make this a reality. And I know that's something a lot of different organizations struggle with. So, hard problem all in all, particularly because we are dealing with a new technology. So getting into kind of that new technology and the different pieces that exist, I'm going to take a little bit more of a technical approach to this now, which is we understand the business need of taking some problem and then productionizing a solution for solving that problem. But when we look at that from a data perspective, what are the stages? And so it starts, we have to set up the problem, and I'll go through what that looks like. We have to do what's called data collection and exploratory data analysis. That's what EDA stands for. So understand the data that we actually have, understand its value. We have to go through data preparation. So actually constructing the problem in a fashion that can be machine readable and solvable by a machine learning algorithm. We then need to select an algorithm and train that algorithm. There are an infinite number of possibilities on what can be done there. Then you need to evaluate the results, and not just the results as it pertains to, a lot of times when you're dealing with modeling, people think of accuracy. Well, accuracy isn't always the most important thing, and we'll talk about that. And then finally, what does that deployment path look like? This stage can be broken into kind of, or these 6 steps can be broken into 2 key parts. The first is what we call data wrangling, and the second is machine learning. So I often refer to these as art and math. How you set problems up is an art form, because there are an infinite number of ways you construct data to actually solve a problem. And then there are some ways that you can effectively ask a computer or machine learning algorithms to mathematically optimize a model to that data. That's all math. It can do all of that without a bunch of human input in many cases. And often this is an iterative process. So a lot of times what you try initially doesn't work. And as models continue to learn, you need to optimize them over time. So even the best model, when deployed for a matter of months, will likely need retraining. So let's get into the problem setup phase. There are 2 key different types of ways you can build a model. The first is prediction. The second is inference. In the machine learning world, these are referred to as supervised and unsupervised machine learning. So prediction being supervised, meaning I know what I want to predict and I have examples of that. Inference being unsupervised, and that I'm not quite sure what I want to predict, but I know there's something there. And so if we get one level deeper, the types of prediction models are generally referred to as regression or classification, and we'll talk about what those are in a second. The types of unsupervised or inference-based models are clustering or anomaly detection. So clustering is, I have a data set and I want to find groups of data in that data set that are similar to each other. And anomaly detection is, I want to find outliers in my data set. Now, described like that, it seems at face value fairly simple, but there are so many shades of gray on how all of these things can be done. And the nuance is really important when you get into actually solving the end business application and what's valuable for the business unit itself. So focusing on the supervised side of things, and when I say supervised, again, what I mean by supervised is we have in a data set an objective and a target that we want to predict, and we have examples of that historically. So the one I use that is most frequent, and I think almost everybody can relate to, even outside of oil and gas, is the stock market. If I wanted to build a model to predict the stock market, which is really hard, and I do not recommend it, but if I wanted to do that, I have a bunch of years of history of what's happened in the stock market that I could learn from and go and build those models. Now, if I want to build a classification model versus a regression model, I need to understand a little bit more about my data. So when we're looking in the machine learning and actually building these models, generally what we want is structured data. And when I say structured data, I'm referring to things that are tabular in nature or could fit into Excel. The most common file format you hear is .csv in the machine learning world. So a comma separated values file, and it looks something like this, where all of your variables, or in the machine learning world, they're called features, are your columns, and all of your data points, each unique data point is a row. And so at the end of that, there is something that I will want to predict. And so let's say in this case, I'm trying to predict this purchased column, and it is a bunch of zeros and ones. This is an example of classification, meaning that there are only two options and there are a discrete number of options that I want the model to predict, or discrete number of categories I want the model to predict at a given time. Regression is similar, but instead of having discrete values, this is, I want to predict a floating point numeric output. So I want to predict some number, and it could be of any range. And so how these problems are set up in the machine learning world is slightly different. The key call out being classification, there is a discrete number of categories. Regression, you're predicting a number, and it could be on any range. And so when you're actually setting these problems up, the best way to think of machine learning and what the algorithm is going to do is, when you have the data set up like this, it does, in algebra, it was y equals mx plus b. It is effectively fitting an equation that says, can I use the variables that are not my target, so that are not my objective, in that row to predict what is happening inside of that row? And so think of it as the left side is effectively just trying to predict what is happening on that right side or in that purchase column. And that is going to occur for every single algorithm in the supervised setting, where it's using the contents of a single row to predict the value in that single row. So that's how we'd set up a problem. And we're going to be focusing primarily on regression and classification today. Unfortunately, I don't have the time to go through all of the different options. That would be the 5-hour extended webinar. But once we get through that, next is the data collection and exploratory data analysis. So you have to understand the quality of your data. Just about every customer, every person I talk to who's interested in machine learning says, well, we have bad data. And you would expect somebody in my shoes to say, oh no, we can't do anything. But the reality is everybody has bad data. Nobody's data is perfect. Data is just our best approximation of trying to represent the real world and gathering information about it. You're always going to have things that are missing values. You may not have sensors exactly where you want them when it comes to doing things like predictive maintenance. But really, in the EDA section, you have to first understand, do we have data that's relevant to what we're trying to solve? Example here is, if I'm trying to predict the stock market and all I have is weather data, I'm probably going to have a bad time and be very wrong. So make sure that I have data that's relevant to the problem, and then look at that data, understand if it has a representative distribution of what you'd expect to see. So there may be some subject matter expertise required to understand the data. And then finally, try and identify, before you even get into the modeling, what limitations might exist in your approach. At the end of the day, machine learning algorithms are perception based. They can only make predictions based on what they see and based on the data that they're given. So knowing what limitations or what's not there is almost equally as important as knowing what is there. Once you get through that exploratory data analysis, you feel like you have the right data, you feel like you understand that it's probably useful for solving this problem, the next step is data preparation. So this is, do I need to clean this data up to make it readable for a machine? And so there may be, for example, set point control data that I have as a part of a data set that is not valuable whatsoever for any machine learning modeling. So if I was building a model for predictive maintenance and I had a column in my data set that was the same all the way through, I'd probably want to remove that column because there's no variance, there's nothing a machine learning algorithm can pick up on. So I can drop columns, or maybe I want to drop outliers. Very frequently, sensor data, instead of being blank when it's broken, says -999, which from a machine learning perspective, a mathematical model doesn't know -999 is any different than 70 degrees C. It just well, it knows that it's a significant numeric difference, but it doesn't know that the sensor's broken in one of them and it's not broken in the other one. And so maybe I want to look for things like that and say, well, I want to remove those data points, or I want to take those and replace them with an average value. The next thing that we want to do is transform that data. So first, we're going to remove things that may not be useful for modeling. And you can really think of it in that y equals mx plus b context, where if you had to build a simple linear model on top of this, would it work? The next is normalization and transforming that data. So you may want to do things like scaling numeric values. And when I say scaling, what that means is likely putting them in some range between 0 or 1 or -1 and +1. You effectively take a whole range of values and make it very constrained and fixed. And the reason why you do this, and there's a ton of different processes for doing this, that many of them are open source. If you know Python or R, you can do all of these things. But the reason why you do this is if I'm building a model, let's say on a furnace, and one of the measurements I have is a temperature of the furnace. And so that's something that can be really hot. And the other measurement I have is a current reading from a certain part or a certain electrical component. So one of them, it could be a few hundred or 1,000 degrees Celsius, and the other one could be 0.000006 or like 60 milliamps or 6 milliamps. I don't remember how many zeros I said. And if you take those and just put them next to each other, one's way bigger, one's way smaller. It's really challenging. Like one of the big one's likely just going to completely dominate the small one because it makes really big changes. The small one makes really small changes. You want them to be treated equally when you're actually trying to learn from that data. And so that's why you do things like normalization. You can also do things like creating new variables. So if I know there's a relationship between pressure and temperature, I can perform an operation and actually create a new variable related to those that may be more useful for modeling. And then the last stage is dimensionality reduction. This is by all means an optional step, but looking and seeing if there is a way to condense all of my different variables into a smaller form factor so that we're only getting the relevant pieces. This is where technologies like principal component analysis, linear discriminant analysis, even things like autoencoders can be useful. I won't go too in the weeds there, but for some of the experts on the call, we can definitely come back to that section a little bit more in the future. So as an example, let's look at our classification data set we were talking about earlier. Some of the things that we would want to do here is first thing, you have a user ID column. This user ID is probably not useful for machine learning because there's nothing in this user ID that indicates if a person is likely to have purchased or not. So we can drop that column. And then we look at this gender, and this gender column is male, female. One of the challenges with machine learning algorithms is they like math. So they only deal with numbers, not letters, contrary to what I learned in calculus 2. And so what we need to do is we need to transform this gender column to something that is mathematically operable. So maybe we create two columns, one is male, one is female, and we put zeros in the ones where it's in the male column, we'll put zeros if it's female, and we'll put 1 if it's female, and we'll put 1 if it's male, and 0 in the female column. But there's a lot of different ways of doing what's called encoding of categorical variables. We'll then take these two columns, which are vastly different from each other, and scale them between 0 and 1 so that they can be treated on an even ground by any machine learning model that we do. And then we can start building our prediction. But, to kind of practically put that forward as a data scientist, I often have to think about how I want to do all these things because it's not always the most intuitive, and there's a lot of experimentation. I've presented one path forward, but there's likely more that can be done here. And so we're about 30 minutes in, and I want to pause for a second, not yet for questions, but to say, like, if you're starting to get worried and saying, whoa, I thought you said this was a session about you can do this yourself. It still is, I promise. But it's important for you guys to understand what the steps are, so that way when somebody else automates them for you, you actually know what's happening under the hood. The next thing that happens on data preparation is splitting of a data set. When you build a model, you often want that model to generalize to the real world. You want something that will actually work on new and never before seen data. And so how this is done is most data is broken or should be broken into what's called a training set and a test set, or a validation data set. And so you learn from the training set, and you only judge the performance of that model on how it performs on that test or validation set. So that way you're really judging it on new and never before seen data. There's a lot of different ways of doing this and different ways to shuffle data and stratified splitting of data. But the overall purpose being, we always want models that are going to be generalizable and valuable outside of this academic setting of experimentation. And so making sure that you actually split the data up and only measure the performance of the model on data it's never seen before is paramount. Next up is training a model. So we have our data, it's all set up and ready to go, and it's perfect in this floating point matrix of just mathematically operable things. And now we want to build a model and try and actually solve this problem. So what do? Do we want to use a linear model or a linear algorithm? Do we want to use a neural network because they're really sexy? Do we want to use something like a random forest or a decision tree? Do we want to use different optimization techniques to try and make this model slightly better? There's a lot of different things you can do here. And what you select, without having any time to go into the nuanced algorithmic details of what's better for what type of problem, there is a huge open source world out there that helps guide you on if you want to use a linear model versus a tree algorithm versus a neural network. What we commonly see is most people just use what they're familiar with, and that's not necessarily a bad thing. So I've selected my model, and then I want to go and I want to train this model. So I train the model when this is a common fit call, and what's actually going to happen is the model is optimized to the data set and the objective that we've defined. And now I want to evaluate that model. So the first thing when you're thinking about model evaluation, I talked about this at the beginning, a lot of times you just think, all right, let's look at the accuracy and call it a day on my validation or test set. But in reality, that's not always what's important, right? Just having a high accuracy isn't really a key thing. And the example I use is if I'm a telecom company, or let's say I'm an HR group, and I want to predict which employees are likely to leave. So which employees are likely to go somewhere else in the next 3 months. I'm willing to accept 10 false positives for every one that I get right, so I can actually work on retaining my high valued employees. And so that evaluation criteria is very different than just a pure accuracy, because I'm very comfortable being wrong, so long as I'm right in some cases. And so we want to say, has the objective been met? And if the answer is no, we may go and try a different algorithm. We may try different hyperparameters. So these are all of the different knobs and levers that you can actually modify within a given algorithm. You might try to ensemble things. And if that doesn't work, you do some experimentation there. You may have to go back and say, well, let's try setting up the data a little bit differently. Maybe we were filling in missing values with the average last time. Maybe we want to try and fill in missing values with the median this time. We can try and create more features. There's a lot of different things you can do, but this is all a part of that experimentation process. Or last ditch resort is we can go and try and find more data. Are there other things that we can actually add to achieve better results per the business outcome we're actually aiming for? So all in all, this is an iterative process. It goes for quite some time. And at the conclusion, you can say, yep, we are all good. This objective has been met. At which point you have to move to deployment. And deployment only gets one box here, but it gets a lot of time within an enterprise. So deployment often takes much longer and many more touches than the model building experimentation. And the reason why is you are building a full-scale application and product when you're deploying these models. You have to create pipelines between data sources. Let's say to build your model, you're pulling data from something like an OSI soft pi. You're also pulling data from a unique SCADA system that doesn't necessarily plug into OSI soft pi. And you may be actually pulling data from a manufacturer about mean time between failures for different devices. And so you actually have to build those data pipelines that is able to pull all of these different data sources and consolidate them. Then you need to focus on the architecture. So it's a software engineering problem. Where do you store all of this data that's being pulled? How do you actually treat it? How do you run that data through a model and store the results and build that application? And then finally, how do you actually monitor for new data? So when do you decide that you want to retrain this machine learning model and continuously adapt this system so that it learns? Maybe you do it every day, maybe you do it every week, maybe you do it every month, or maybe you only do it when you see certain components of data drift, which is something that you can monitor inside of these production systems. So at the end of the day, we've just gone through step 1 to step 6. So everything from what do we want to do to deploying that model. And we've done it in about 35 minutes. In the real world, it takes a little bit longer, probably about 40 minutes. I'm kidding. This is something that in most organizations takes a matter of weeks to months, in some cases years. And so we are barely scratching the surface of how this traditionally works. But what I've just shown you is, for the most part, the things you need to understand what a machine learning system looks like end to end. And so, even though this often takes a lot of time, the overall steps are not necessarily that complex when you break them down. The good news is there's a technology that has become much more popular in recent days called AutoML, or automated machine learning. And so pretty much almost all of the technical mathematical pieces I talked about, there are tools out there that can help you automate all of the things like how to prepare a data set or how to clean a data set, which algorithm to select, how to train it, how to evaluate that algorithm based on what you actually care about. And there are all sorts of tools out there that exist to help do this. So some common AutoML tools and platforms out there. So I make the distinction between open source tools and platforms because the ones on the right are paid, the ones on the left are free. But you have, if you're familiar with Python or R, there's AutoSKLearn, Teapot, AutoKeras, H2O, SMAC. One that I didn't talk about on the left-hand side that I should have is called Weka. It's WEKA. They have a really good free AutoML platform. It's out of New Zealand. So if you want to play around with it, I would actually recommend using Weka initially because they've been in the game for a very long time. And they also have a lot of tutorials and documentation on how to get started. On the right-hand side, there are a lot of companies that have kind of sprouted out of this AutoML concept because they see that there's a huge market for people that know their problem but don't necessarily know the data science steps to resolve this problem. And so you have companies like Data Robot, H2O, Darwin, Spark Cognition. So some of the work that I've been doing. If you guys want to ask questions about those, we can definitely come back to them. But want you to know that there's a lot of different options out there. So before I move to the next section, which will take about 15 minutes, I want to cover some of the questions that have come up. So there was a question about how important is encoding. So when we're talking about handling categorical data, and my answer, unfortunately, for almost every machine learning question is it depends, because it does depend on just about all of the different data components you're looking at. And so how important is encoding? So is it important to encode data? Yes, that data is not going to be useful for a machine learning algorithm if it is not encoded into some numeric format, and categorical encoding, notably. However, how you do that could depend. There's probably 7 or 8 different well-recommended approaches for encoding. And which one you select can have significant impact on your model, but also if that particular column or that particular categorical column doesn't add a huge amount of signal or predictivity to the problem, what encoding type you select doesn't matter. The next question is, what if we don't split training and test data? What if I use the data set as both train and test data? Really good question. So can I train and test on the same data, and can I use that to identify if my model is accurate or not? The answer is you can try, but what I equate that to is if you go and you, for example, let's say I'm in a college class and I need to, I have a test the next day and my professor gives me a practice test and I learn all the answers of the practice test. There's 2 ways I can do that. I can learn the content and I can actually understand, okay, I understand this relationship. I think I could answer this question if it was asked a different way. Or I could just learn the answers. The answers are A, B, B, C, C, D, D. And if you don't actually have a separate validation set, you never have a guarantee that your model's not just learning the answers and not the relationships. And so we always recommend using a validation and testing data set for anything that's going to make it to production. If you want to look good, sure, use the training and testing data simultaneously, but there's no real business practicality to it. Few questions. So do I need to learn a coding language to succeed in machine learning? Absolutely not. That's why I actually recommended Weka. If you want to get started, Weka has a drag and drop set of functionality. There's also free versions of tools like RapidMiner that have drag and drop setups for learning machine learning and using machine learning algorithms. We absolutely at Spark Cognition have a user interface focused, and I'll show this here in a second, option for building models in machine learning. If you want to get really in the weeds, so you want to set up your own neural networks and train them in very nuanced ways, you likely will want to learn Python or R, but you do not need to know how to code in order to actually succeed in machine learning and build good models. So last question I'm going to answer before I keep moving is there's a question about what are the things we look for in a good model? How do we decide if the model reflects reality from my data set? And this is where understanding, and this is one of the biggest challenges data scientists even have, is how do we know if the model's good enough? And the reason why is when you are training a machine learning model in the weeds, you are effectively saying, take this data and fit some mathematical function to achieve some mathematical objective. So the objective has to be quantifiable, or else machine learning can't actually learn how to do it. Now, how we do this is we will say, pick it's called a fitness function. And so in a classification problem, that could be accuracy. I care about how many predictions I get right over how many total predictions I make. But there are other things that you can look at and all sorts of different scores you can use, like F1 macro, F1 micro, ROC, AUC, precision, recall. And so understanding how those fitness functions that are effectively those mathematical optimization objectives relate to a business problem is absolutely something that you will need to understand. The good news is you can generally say, hey, I have this type of problem. What fitness function is recommended? And somebody on Google's already answered that for you. However, if you want to understand what these fitness functions are and how they operate, there's generally 2 or 3 sentence write-ups that get you everything that you need to know without having to dive into exactly how they're calculated. So I'm going to keep moving. I know there's a lot of questions on the chat or comments on the chat. So I apologize if I'm not able to get to just about everybody's. But if you do have particular questions you want me to answer, please ask them in the Q&A section, and I'll do my best to get into all of them at the end. So let's go through an example. So first thing is, how do I know if something's even a good machine learning project? And so I'll call this the Keith framework for actually looking at this. And is there a substantial business outcome that can be achieved? Do I have data? Is this a project that needs machine learning? If I had a person doing this full time, could they do it well? And can I define success? So we'll walk through each of these with an example. And actually, I know there's a lot of geologists on the line, which I'm very grateful for. I'm not a geologist. Just point blank, if I say anything stupid, I apologize in the field and domain of geology. I am a mathematician and machine learning proprietor. But let's go through an example where I have a bunch of well data, and maybe I think that there's a problem we could solve, or we could actually, based on drilling data and measurement data, we could create predictions about what sort of rock strata that we are digging through. So this is an open source problem that was on GitHub. I believe it was the Society of Geological Engineers that actually posted this this question in this project. But the first thing is like, okay, is this a good AI project, or is this a good machine learning project for us to invest in? And so let's go through each one of these. So is there a substantial business outcome that can be achieved? And so the problem again is, can we automatically predict reservoir lithology? So is there an outcome that can be achieved? And so the answer to this is I may say, okay, well, if I'm able to predict rock type in real time, I'll be able to optimize drilling and that's good. Yes. But unfortunately, like when you're talking about building a business case, like saying something is good or it's going to be better, those are not quantifiable metrics that are that useful. So if I have to go and make a case to management that we need to spend $250,000 of time and resources on this particular problem, we need to say, here is what we think we can save, or somehow quantify that. And so we could say, all right, well, purchasing and maintaining wire logging and measuring equipment to support additional wells can cost over $1 million per site. We have a lot of different sites. If we have something that can use the data that's already being collected at all of those sites, and we will not have to go and buy more measurement equipment for some of the new sites that we're standing up, that's a huge value to us. And we can actually project over time what that looks like based on history. And so, okay, yes, we think that there is a measurable business outcome that can be achieved on, we will not need to purchase as much measurement equipment moving forward if we can do this automatically on equipment that we already have at a drill site. Okay, great. So do I have data? In this case, yes, there's well log data from Hugoton and Panoma fields. And so we have data that exists, and this is going to be traditional logging data from a drill site. So it's going to be things like depth, things like gamma ray, et cetera, relative position, really common measurements that can occur. And most organizations will have this type of data. But let's say for this particular problem, because I have it all set up, yes, we do have data. So the next question is a fun one, which is this a project that needs machine learning? These are some of my favorite questions that I get, because I'll have all sorts of problems presented to me and they'll say, hey, I need machine learning to tell me what parts are needed to repair this particular problem. And, I look and I say, well, is there a repair manual? And they're like, yeah. I'm like, okay, well, does it tell you what parts are needed? And they're like, yeah. I'm like, well, then you don't need machine learning. You can just read it. Or you can build a filter that looks for it. So where is machine learning valuable? Machine learning is valuable when you are trying to synthesize a lot of data and either infer data that you don't have in what is commonly a complex process, or there are a lot of heuristics that can be used to try to solve a problem, but those heuristics fall short of the overall objective. And so in this case, I went and found, is there a way to actually predict reservoir lithology at given points? And it turns out, yes. In the petrophysical handbook, there's a fairly complex process that is used to try to identify what the lithology may be at any given point in time. And it's fairly human intensive. And so, all right, this is something we think we can do better if we just have more real-time data and some examples to learn from. So yeah, this is a good project that needs machine learning, because there is this complex series of heuristics that are stacked together to get something that is approximately okay, but not that great. And then finally, if I had a person doing this full time, could they do it well? The reason why I asked this is to try and ground a lot of the management I speak to with reality, which is, if you have a problem and you don't think somebody looking at that problem all the time, every day, let's say in a very thin slice, could solve that problem, it's very unlikely that mathematically there's some magic that occurs that makes it feasible. The problem with what we're talking about here is that, yes, there is a person that can do it, as we just talked about on that last section, but it's a very intricate process that requires a lot of time and expertise. And so, here is the process that person will have to go through. And if we had one person for every well, they'd probably be able to do this fairly decently, but we don't. And so, this is a good fit for what machine learning can do. And then finally, can I define success? You need to identify or break projects into phases so that you can really quickly show wins. Most customers I speak to, and almost anybody I go to, saying, can you solve this problem? It's like, yes, we likely can, but it takes time in a lot of scenarios, because you have to do all this experimentation and understand the data. And so the first thing is, like, can we predict something that is equivalent to a heuristic system? And so we want to break it down into chunks that are manageable. Like, can we get something that is accurate as what exists today? And we'll say our objective is 85% because heuristic systems are 60%. All right, phase two is, okay, well, once we're able to prove that this is feasible and we can do that quickly, let's go and see if we can do this in real time. And so in real time, we can actually create these predictions, and it will be information that a drilling engineer can use. And then phase three is, well, if the drilling engineer can use it, can we learn from the drilling engineer and build an optimization system around that to actually use this information more effectively to modify, rate of penetration, weight on bit, all these different things that can actually be done. And so let's say we can break this into kind of a 3-phase project to make it successful and also approachable and manageable for our organization. So let's go through a demo really quickly. I'll show you a quick 3-minute tour of how you can do this in an AutoML tool. So I'm going to show you guys our Darwin product. Again, there are a lot of different things out there for actually solving these AutoML problems. I'm showing one example of how to do that. But let's say, I have my data set for my different fields. Let's go and create a model. And so I'm going to call this rock prediction model. And so then it says, all right, well, now I need a data set. And so if I need to, understand what that data set looks like, it shows me an example and says, I need my variables or my features. I need my objective. Okay, well, I can upload something from my computer, or in this case, I have already uploaded a Rockstrata training example. Click next. And then it presents to me some green, yellow, red options. It says, well, every single variable is automatically analyzed by the model builder. And it says, okay, there are 10 columns that are ready for model building. There's one column where you may need to make some decisions on it. So whether it's how encoding occurs, how you fill in missing values, whatever it is. And there's 0 columns that are not useful for model building. This is great. This is a fairly clean data set. So I can go and I can actually look at the data set itself. And as you can see, it has what we're trying to predict here. So here are the facies that are being predicted. Here's the formation, the well name, depth, gamma ray, all this information about it. And then there's one recommendation over here that says, hey, we noticed that this column may be categorical. And it's already said we're going to treat it categorically. If I wanted to treat it as a number, I could go back and make that change. But let's say I don't want to make any changes. I can say, all right, great, let's go build a model. And then I say, let's predict this is my target column. So I have to select what it is I actually want to predict. And I say here, this facies column is what I want to predict. Click next. And it says, all right, we're deciding between regression and classification. Again, regression is predicting a number. Classification is predicting a category. And it says, we've noticed that this column has 9 categories or 9 classes. Is this correct? Yes, that is correct. Is this a time series problem? There's some complex things you can do with sequential data, like testing out different types of neural network architecture, changing how you perform that train testing split, and modifying how missing values are filled in if it's a time series problem. But in this case, no, it's not a time series problem. We're going to create an individual prediction per data point. And then the last thing is I just say, all right, this is an infinite search problem, meaning there's an infinite number of mathematical possibilities that can be tried. Darwin's going to try and intelligently identify the best place to start and which ones to try first and how to continuously learn from those experiments and get better over time. But how much time do I want to give it to actually try and build a good model in this data set? Let's say I gave it 20 minutes. And this is actually a data set where the more time and more experimentation you go through, the better the model gets over time. And so I can go and specify that I want it to build for 20 minutes. I can modify some advanced parameters if I want, like what is that fitness function? And it even tells me here is why I would want to use some of these different fitness functions or objective functions based on what they are. But let's leave it as the standard for now, and we can go ahead and start model building. So what's happening behind the scenes here is we are taking that data set and experimenting with a few dozen models, figuring out what works best, what doesn't work best. And within this product, we're primarily looking at deep learning models and decision tree-based models, seeing what works, seeing what doesn't work, and then taking the characteristics of models that work, promoting them, and iteratively building more and more models over time. So after 20 minutes, I've probably gone through a few thousand models and created a lot of different predictions. And at the end, I will have a single model that is the best fit for my particular problem. So I built this model for just 10 minutes about an hour ago. And as you can see, we did pretty well. We were able to saw, much better than that 60% heuristic, but still not quite as high as the 85 or 90, 95% heuristic that we'd be aiming for. And so I can see the accuracy of the model. I can see metrics like precision, recall, F1, things that are all kind of further explained if you want information on them. But I can also see things that are really important, like what drives predictivity. So can I actually look at a feature importance of what drives predictivity? Can I look at how we perform in what's called a confusion matrix? So what do we predict and what actually happened? And how accurate are we, or how well do we do for a given category? And so as you can see, there are certain categories that we predict more accurately than others. Like, for example, this mudstone category, something that we probably would look to improve, but there's also not that many examples. And so I can go and I can learn all these things. And then the last piece is, let's say that I thought this model was ready to go and ready for deployment. I can actually go and I can download it. So the whole model is downloadable as an executable file to where it can be embedded into an application. And then I would just need to feed data to it. And all of those cleaning steps we just went through, all of the scaling, all of the categorical variables, all of that is automatically handled. It is then scored through the model and predictions are generated, just as if you're calling a single executable. And I would imagine most of you are familiar with just double clicking an executable. That is similar to how this deployed downloaded model works. And so I can really easily go from this idea and some data set that's good into something that is all the way ready for deployment, and everything is packaged up neatly for my application. And so this is, for the sake of time, this is one example of how you can go and automate model building. But there are a lot of different tools out there that help you do this. And not all of them require coding expertise. So I'm going to pause for a second because we only have 5 minutes left. And I think there's a few questions that we may want to get answered. So let me pull the slide deck up and let's go through some of these questions. How can I get any of these automated machine learning tools free online? If you search free AutoML tool, there's going to be a lot of different things that show up on Google. I've called out a few of them. I would definitely recommend, if you're looking for a place to get started, try out Weka. If you are familiar with coding, then I would try out something like H2O, or possibly RapidMiner, which has a free version as well. But would absolutely recommend just trying and searching a few things. There's probably tools I'm not even familiar with that are fantastic. There's a question about how you would appropriately validate data if you have limited training or unconstrained data. It's really hard to appropriately validate if you have limited examples. And so particularly when we're talking about problem types like predictive maintenance, what I just showed you is how you build models in a supervised setting, meaning I have a lot of labels and I know what those labels are. In problems like predictive maintenance, you don't have a lot of labels. And why I say that is because there's generally not a lot of failures, and a lot of example data you have of failures. You're not in business for too long if there's a lot of failures. And so there's different approaches that you can try to mitigate that lack of labels. You can try balancing your data. You can try adding significant weight functions to where failures are treated much more with much more gravity than non-failures. You can also try semi-supervised or unsupervised approaches like normal behavioral modeling, clustering, anomaly detection. There's a lot of different things that you can do for that. So a few of the recent questions, basic knowledge or background for machine learning. There's some really good blog posts out there. If you look for intro to machine learning, I have some of my favorites, for example, blend comedy with machine learning. I can maybe send those to Annabella afterwards, and she can distribute those or as needed or as decided. Or if you reach out to me directly, I would be more than happy to send you some of the favorite things that I like to read and like to send people. There's a question about what accuracy or what measure of accuracy do I recommend for classification? It really depends on the problem type. Generally, if it's a fairly balanced problem, meaning I have a similar number of samples for each class, I recommend an F1 weighted score. If it is a heavily imbalanced problem and I care about predicting the minority class, or the one that occurs less frequently, I often recommend using something like an F1 macro. But it's really hard to answer that appropriately because there are so many different metrics that can be used. So maybe one or two more questions. You know, with regards to the product that I just showed, you know, what's different about it? You know, I personally, it's near and dear to my heart, but from AutoML tools, it spent a lot of time focused on usability. So anybody can actually pick it up and use it, and it will coach you through that model building process. And then on the back end, it's using some of the most complex technologies for example, neuroevolutionary approaches to build optimal neural networks or optimal decision tree based models. So there's a lot of really cool technology that goes into this stuff. Let's see.
All right, so we are at the top of the hour. I want to thank Keith for sharing all this knowledge with us. I want to thank all of you for attending. The webinar will be made available through the Energy and Data webpage, the exact same place where you went to register. It will have past webinars. Please don't forget to register for the upcoming webinars. We will have one webinar a month, and in the month of June and July, we will have 2 webinars during that month. We want to see you all at the annual event, February 21 through the 24th in Austin. We look forward seeing you there and seeing your contributions. Again, thank you for attending. The webinar will be made available, and I have captured the questions on the Q&A chat. Whatever was not answered, Keith can go over later and email each participant and answer those questions. He has his information on the thank you slide. You may also take note of that. And Keith, if you're available to answer extra questions that are sent directly to you and you don't mind, otherwise you can channel them through me and or the Energy and Data side, and we will be more than happy to answer your questions. So hopefully we will see you at the end of next month on our next webinar. Thank you, Keith, once more for your wonderful presentation.
Awesome. Thank you guys. And thanks for, the fantastic engagement and questions. I really appreciate it.
Thank you all. Bye.